thank the organizers for inviting me to give this review on Jackiw-Teitelboim gravity, or JT gravity. So let me start by giving you a brief outline of my talk. So I'll first start by giving you an introduction into generic 2D dilettone gravity models. And then I will discuss, as a specific example, Jackiw-Teitelboim gravity. First, I will discuss its classical gravity aspects, the classical solution, and its description in terms of Schwarzian quantum mechanics. Then I will describe the quantum features of this model, in particular, first amplitudes on the disk partition function, and boundary correlators and their interpretation in terms of gravitational physics. And then in the last part of my talk, I will discuss higher topology. I will discuss the calculation of these amplitudes from a gravitational perspective, and then from a dual matrix model perspective. And in the end, if I have time, I will mention some recent examples. Okay, so let me first discuss some generalities of two-dimensional gravity. So suppose our goal is to find interesting models of gravity in lower dimensions, and in particular in 1+1 dimensions. Then the simplest example you might think of is the Einstein-Hilbert action, but that one is topological in 1+1D, or in 2D. It's just the Euler characteristic, which means that every metric in the same topological class has the same value of the on-shell action, and there's no sense of extremizing the action and getting interesting equations of motion. So then you might think, let's just add matter to this action. Maybe then things get interesting. So just take Einstein-Hilbert plus the matter action. But then, of course, the Einstein equations just lead to a zero stress tensor for the matter sector. So no energy can be consistently added in this way. So this is not useful as a classical toy model of, for instance, black hole formation and evaporation and so on. So we need a different coupling to the matter sector. And an answer to this question are the 2D dilettone gravity models, where I introduce an additional scalar field phi that I call the dilettone field, and it couples directly to the Ricci scalar in this way. I also allow for an arbitrary dilettone potential v of phi in this model. I have a matter action if I want, and then if I define this model on a manifold that has a boundary, there might be a possible boundary term, like a Gibbons-Hawking boundary term, and that is indeed what we will have in the discussions later on. So as a specific example of these generic 2D dilettone gravity models is Jackiw-Teitelboim, or JT gravity, where I pick a very specific form of the dilettone potential that is linear in the dilettone field phi. So the potential is minus lambda times phi, where lambda is a cosmological constant. Now, I will be interested in asymptotically ADS versions because I want to do holography. So I will pick lambda to be a negative constant in suitable units -2 here. And then the action can be written like this. So this is the JT gravity action. So phi times r plus 2. So the dilettone potential has been introduced here, the linear dilettone potential. And then a Gibbons-Hawking boundary term, which I've written very explicitly here for the asymptotic ADS boundary. Now, there are several motivations for studying this particular model of dilettone gravity. So let me briefly mention these. One of these is that you get this precise model as a dimensional reduction, so the spherically symmetric dimensional reduction from 3D pure gravity. A second motivation is that this model appears quite universally as the near horizon theory of near extremal higher dimensional black holes. So there's a universality argument here. Thirdly, and this is how it appeared in the last couple of years, in particular since Kitaev's talks in 2015, it describes the low energy sector of all known SYK-like models. And then finally, I've already mentioned this, I defined this version, or the ADS version of this model, which means that we can use it as a toy model to study or to learn about holography. So now that I've introduced the model, let us think about the dynamics of this model. So first at the classical level. So let's think about the classical equations of motion you get from this action. So if I vary this action with respect to the dilettone field phi, so then, well, the answer is very simple. I just get r equals -2. The Ricci scalar is fixed as the equation of motion. Now, in 2 dimensions, there is only one curvature function, which you can conveniently parameterize as the local Ricci scalar r of x, so that if you know r of x, you actually know everything about the local geometry. So knowing that the Ricci scalar is -2, we know everything about local geometry, which means the geometry is fixed as some patch of the ADS2 manifold. So I've written the metric of the ADS2 manifold here in Poincaré coordinates, where I call big Z the Poincaré radial coordinate, where Z is 0 would be the holographic boundary, and big F would be the Poincaré time coordinate. Now, there are several known frames on the ADS2 manifold that are important and that I will need. So let me briefly mention these. So it's convenient at this point to transfer to light cone coordinates. So big U and big V are the two light cone coordinates of the Poincaré coordinates. So big U is time plus radial coordinate and big V is time minus radial coordinate. And then you can write the Poincaré patch in these Lycon coordinates, of course, in this way. And you find this, this metric or this patch of the ADS2 manifold directly in the near horizon regime of higher dimensional extremal black holes, as is well known. But there's also another patch on this manifold that we will encounter later on in this talk, which I will call the black hole frame. And you can get this by using a coordinate transformation purely on the light cone coordinates. So I define big U as a function of small u and big V as a function of small v by using a hyperbolic tangent transformation here that is parametrized by this parameter beta, which will of course be the inverse temperature of the black hole. If you plug this transformation in the Poincaré patch, you get this metric. And this metric directly is found, or this patch is found in the near horizon regime of higher dimensional near extremal black holes. Now, to see that this is a black hole geometry, it is convenient to go to a different radial coordinate, which I call r, which is related to the radial coordinate in these null coordinates by using this hyperbolic cotangent transformation. Going to this radial coordinate, you find this typical black hole form of the metric, where r equals rh would be the black hole horizon. So this is indeed a black hole solution for which you can calculate the total mass in the bulk space-time. And you find that this is proportional to RH squared, so the horizon radius squared. And you can also calculate the Hawking temperature by demanding that the Euclidean section of this manifold doesn't have a conical deficit. You find that the Hawking temperature is proportional to RH, which immediately leads to the black hole first law of this classical solution, where the Hawking temperature is proportional to square root of the mass of the black hole. And this formula will be important later on because we will actually be studying the quantum extension of this. We will find this in the classical regime of our partition function later on. And just to show you the Penrose diagrams of these different frames. So this bigger triangle here that I show you here would be the Poincaré patch with the extremal black hole horizons and the boundary, the holographic boundary on the right. And the smaller green triangle would be the black hole patch that is contained within the Poincaré patch. I've also shown the global patch here, or the global frame, which is a strip region in ADS2, but I won't be needing that during this talk. Okay, so now let's imagine inserting this action in a path integral calculation. Then the first step we can do, or we should do, is we should path integrate out the dilaton field phi. Because it appears only linearly in the action, this serves as a Lagrange multiplier, and it forces the Ricci scalar to be constant also off shell. So not just classically, but also fully quantum mechanically. Now, once you have done that, the bulk piece of the JT action is gone because that just became a delta functional, and only the boundary term survives. Only this Gibbons-Hawking boundary term survives. Now, to find interesting dynamics, we have to impose boundary conditions on this model. And to impose the boundary conditions, we will consider a boundary curve f of t, z of t, where f and z are again the Poincaré coordinates, and they are functions of t, some proper time coordinate. And we will consider this boundary curve as a UV cutoff that carves out a shape from the ADS manifold. So this curve is very close to the holographic boundary, and it wiggles there, and it carves out a shape from the ADS manifold, and this will be our effective boundary. Now, to specify this curve, we need to impose suitable boundary conditions. The first one, and this is the standard one you use in any case of ADS CFT, is that you demand that this respects the asymptotic Poincaré boundary conditions, which in the coordinates that I have shown you here, implies that z of t is epsilon times f dot of t, where epsilon is the usual UV regulator by moving the boundary slightly inwards that you always use in ADS CFT. So this is the usual Pfefferman-Graham gauge. And in this case, it leads to the one-dimensional conformal group parametrized by f of t of the diffeomorphisms that preserve the Pfefferman-Graham gauge. So this is the standard story you do in ADS CFT. Now, there is a twist to this story in this model, which is that the dilaton field, if you solve for its classical equations of motion, which I have not done here, but so you have to believe me, the dilaton field is actually blowing up at the boundary as well, just like the metric is doing. So this needs fixing, just like the metric. So the Pfefferman-Graham gauge was imposed for the metric, or asymptotic Poincaré boundary conditions were imposed for the metric. We need to do something analogous for the dilaton field. So the idea behind this is that you cannot compare spacetimes that have different asymptotics. So if the dilaton field is blowing up, it needs to blow up in exactly the same fashion for all spaces that we can consistently compare to one another. And we can impose that boundary condition, or we can fix this blowing up of the dilaton by having the boundary follow a constant value and constant and large value of the dilaton. So the dilaton field phi at the boundary is blowing up as epsilon goes to 0, but I control the way that it blows up. So I have this dimensional field parameter A that defines my theory, and I define the value of the dilaton field on my boundary curve as A divided by 2 epsilon as epsilon goes to 0. So these are the boundary conditions. And with these boundary conditions, I will explicitly, or we can explicitly evaluate this Gibbons-Hawking boundary term, because we know that this is just describing a wiggly boundary curve in an ADS2 geometry. The boundary value of the dilaton is fixed to this value, and Z and F of t are related by this relation. So I can rewrite everything in terms of 1 degree of freedom, which is F of t. So just doing the calculation, you compute the pullback of the metric determinant to the boundary curve. You compute the extrinsic curvature trace in an expansion as epsilon goes to 0. After a holographic renormalization step, you find that the Gibbons-Hawking boundary term fully reduces to this action fully in terms of this single degree of freedom f of t. F of t can be thought of the time reparametrization of the boundary of the Poincaré coordinate, or the Poincaré time coordinate big F, as a function of some proper time t. And the Lagrangian itself is proportional to this quantity here, which is the Schwarzian derivative of f with respect to t, so which I've written here. So this is this looks like a complicated higher derivative action for that time reparametrization. And there's a prefactor here that I call big C, which you can get by picking up all of the coefficients in these boundary conditions, which is A divided by 16 pi g Newton. So now let me discuss some of the properties of this action. So this action, we will call it the Schwarzian action. So it fully describes the boundary dynamics of this wiggly boundary curve, and it's the only degree of freedom left in this two-dimensional gravity model. So let's look at this action more closely. So first of all, this coupling constant big C, I've written it again here in terms of the quantities we had earlier. You can distill, or you can get to the semi-classical regime if you let that coupling constant go to infinity, because that basically means that the Newton's constant, or h bar, is going to 0. So this would be the regime where gravity is classical, so the quantum fluctuations of gravity are turned off. I should also mention here that this big C coupling constant has the dimensions of length. The 2D Newton constant is dimensionless, but this A that we chose to define our boundary condition, that one has a dimension of length, giving big C a dimension of length, which means that just by power counting renormalizability, we expect quantum effects in this model to be important in the IR, not in the UV, but instead at very long times and at very long distances. So this is something that we will see later on explicitly as well. Now, given this action, you can easily calculate the total energy, or the Noether charge for time translations, and you find the energy as a function of time is just minus c times the Schwarzian derivative itself. So just the Lagrangian is also the energy of this model. Then we can look at the Schwarzian equation of motion. So we vary this action with respect to f. Then you find the equation of motion stating that minus c times d dt Schwarzian derivative is 0. But minus c times Schwarzian derivative was the energy. So the equation of motion is just energy conservation. The EDT is 0 in this model. Now, this was for the pure gravity model, pure JT gravity. Now, if you imagine coupling this to a matter sector, the equation of motion actually generalizes in a very straightforward fashion. So instead of having the EDT equals 0, the EDT equals the net influx of our matter fields that we couple to our gravitational theory from the holographic boundary, where TVV is the influx of matter and TVU is the outgoing flux of matter. So this means that the total energy is changed by the injection and extraction of matter energy from the holographic boundary. And this equation here gives you a differential equation that you can solve for the time reparametrization f of t, given these sources. And with f of t, you find the full trajectory of the wiggly boundary curve. So the full classical picture of this theory we have is that we have a boundary curve that starts wiggling as a response to extraction of energy, that TUU, these blue lines here, or injection of energy, for instance, these green lines that appear here. For simplicity, I will consider my matter sectors to be a two-dimensional CFT. So this formula was already written, specified to a two-dimensional CFT. There are generalizations, but for the purposes of this talk, this will be sufficient for us. So now let's apply this Schwarzian different.
I'm sorry to interrupt. Can I ask a question?
Yeah, sure.
Yeah, so I was just trying to relate this to what happens in higher dimensions, higher than ADS2.
Yes.
Could you do a similar construction? So what's confusing me is that we don't normally think of the location of the boundary as a dynamical degree of freedom.
Yes.
So usually we introduce this cut of epsilon simply to regularize the theory,
Yes,
and then
yes,
we
yeah.
normalize it, but then we take it to 0.
Yes.
But here you're getting all the dynamics simply from precisely this location.
Yeah.
So could you comment on why this is different in high dimension?
Yes. So this is not a genuine ADS CFT. This is, well, sometimes people call this nearly ADS2, nearly CFT1. So both the bulk and the boundary are not exactly ADS CFT. For instance, the boundary cannot be a CFT because a one-dimensional, a 0 plus one-dimensional CFT, because then the stress tensor trace is vanishing for a CFT. But in 0 plus one dimensions, there's just one component, which means that the total stress tensor should be 0. So that a purely or an exact one-dimensional CFT should not be a very interesting gravitational theory. So conformal symmetry is broken here. And the way it is broken is by the dilaton field phi. You can view that parameter A here as a measure for the breaking of conformal symmetry. If I set that A to 0, for instance, then this Schwarzian action becomes 0 again. So this would restore conformal symmetry. So conformal symmetry is broken in this model, and that's the difference. That's why this wiggly boundary curve is physical.
So I'm actually not so worried about conformal symmetry itself. I mean, that's just one property when you have a specific theory at the boundary and a specific theory in the bulk. Mm-hmm. But you could also look at non-conformal theories. What I would like to understand is whether you could also have these dynamics in the location of the regularized boundary in high dimensions. And if not, why not?
Well, I don't think it's physical. I think so the physics of these wiggles in higher dimensions where you do have conformal symmetry, you can just do conformal transformations to map one configuration into the other. Well, here, because of the breaking, these become distinct physical configurations. I think that's one way of phrasing it. So everything ultimately comes from this one step that I didn't tell you about technically, that if you look at classical solutions here, that the dilaton field is always blowing up at the boundary. And that is something that doesn't happen in higher dimensions.
Well,
so you have a background field that behaves just like the metric in a sense. But the metric is blowing up at the boundary and you need to impose a gauge because otherwise you cannot compare spaces that have different asymptotics. But in this case, this other field is also doing the same thing. Perhaps another way of stating this is that this model from a conventional ADS-CFT perspective is actually more natural from a three-dimensional gravitational perspective than a two-dimensional perspective. If you study three-dimensional gravity and you dimensionally reduce to 2 dimensions, when you impose the Pfefferman-Graham gauge for the three-dimensional gravity, then this boils down to Pfefferman-Graham gauge for the two-dimensional metric as we have here, but also this condition for the phi field, which just becomes like the GRR component, let's say, like the last component of the metric.
G theta theta, yeah.
Yeah, oh, yes, sorry, yeah. Yes, indeed.
So can you say that if you uplift this to one more dimension, that this becomes the Liouville mode at the boundary of the...
It is related to that, and there are many links to be made with Liouville theory, but yeah, I think that's a subtle discussion on, for instance, whether pure three-dimensional gravity really has full Liouville theory at the boundary. I don't necessarily think this is true. I think it has aspects of it, but not necessarily the full Liouville field. Quantum mechanically, classically, it might be okay, yes, but quantum mechanically, yeah.
Yeah, but if you uplift this to 3D, well, in general, you're going to get more dynamics. So
well, there is an analogous action like this for 3 dimensions. These are these Alexeyev, Shatashvili geometric actions for the Virasoro group. Okay. They are the natural 3-dimensional generalization of this, and those actions have the property that they dimensionally reduce back to the Schwarzian theory.
Okay.
Mm-hmm. Okay, so we had this classical differential equation for our frame or our time coordinate f as a function of t, sourced by these matter stress tensors. So now let's apply this to a situation that we would be interested in quantum gravity, which would be an evaporating black hole. So we will consider an infalling matter pulse in the Poincare frame, so TVV, which is the ingoing matter energy, is E0 times delta T. So that's this blue pulse that's being injected here from the holographic boundary, which is on the right. And I will consider matter quantum effects to be included, and our matter is again a two-dimensional CFT, but I will keep my gravitational sectors to be classical. So the matter is quantum mechanical, but gravity is still classical, meaning that I'm just solving this differential equation sourced by quantum values of these matters, of this matter sector. Now I need to impose suitable boundary conditions also for the matter sector in order to simulate black hole evaporation. And the first one of these is that we will have no outgoing matter in the initial state. So the initial state would be like the Poincare vacuum, and there the boundary condition is that this state doesn't have outgoing matter. But because we have to change frame in this model, that the entire dynamics is precisely the dynamics of changing frame, and because the chiral stress tensor in two-dimensional CFT has a conformal anomaly, this means that in another frame, the outgoing component of the stress tensor is non-zero and fully determined by the conformal, which I've written here. And the second boundary condition, and this is the one that will allow us to go to an evaporating black hole, will be that we will impose perfectly absorbing boundary conditions at our holographic boundary here, which means physically that we will choose the observer on the boundary here, on the boundary line, to remove all the Hawking radiation he detects in his local frame, which means we set TVV equals 0. If I don't do that, then a black hole in ADS, where I just send in this pulse and create a black hole, it will equilibrate with its Hawking radiation. So I need to impose this absorbing boundary condition here to extract all of the outgoing Hawking radiation and to allow the black hole to actually evaporate in ADS. So TVV is 0, TUU is given by the Schwarzian derivative of F with respect to T, and then the energy is also a Schwarzian derivative. So I have a very simple differential equation for the Schwarzian derivative of F of T, which just gives you an exponentially decaying function. So the energy of this system, it starts off at 0, then it goes up to E0, which is the energy of the pulse, and then it decays exponentially as the energy leaks from this system by these absorbing boundary conditions. And given this energy as a function of time, you can immediately find this, this time reparameterization. So I just write it here for completeness. I will not need a specific form. It's given in terms of these modified Bessel functions. Now, with knowledge of this time reparameterization F of T, we can actually calculate the early-late matter entanglement entropy during the evaporating process. So this is the calculation that Hawking sort of envisioned in his early papers, and that the AMPS paradox was also addressing well, a couple of years ago. And if you do that calculation in this model, which you can do completely analytically, you find this function for the matter entanglement entropy between the early and late Hawking radiation, which is this red curve here. So it keeps on increasing, which means that there is information loss in Hawking's computation, as we already knew well, from Hawking's papers. Now, it is interesting to compare this to the black hole entropy, which is basically just the Bekenstein-Hawking entropy as a function of time. So this would shrink because the black hole is shrinking. So this would be the blue curve in this specific model. And then, well, an observation you can make here, which of course you can do in any dimensions, if you follow the minimum of these two curves, you get a page-like curve. So you get some sort of entropy that goes up and then goes down again, which is what you would expect for a page curve. Now, what we have learned in the last couple of years is that we need to take this seriously because this corresponds actually to the jump in the minimal quantum extremal, or well, some sort of refined Ryu-Takayanagi prescription, a jump in this minimal surface, where after the page time, we actually need to follow roughly this blue curve that's drawn here. But this requires non-perturbative knowledge in gravity because we need to swap the saddles around. So this is something that we will miss, of course, if we restrict or if we keep gravity classical, which is what I have done up to this point. But this calculation, the better calculation, it has been done in JT gravity, and I would like to refer you to these papers for the details. And it leads to this so-called island rule. And we will presumably hear much more about this on Friday, so I won't go into that here. So this was just to give you an example of an analytic calculation you can actually fully do in classical JT gravity. So next, I want to transfer to quantum JT gravity, and I want to calculate correlation functions, in particular boundary correlation functions of JT gravity or Schwarzian quantum mechanics. And I will do that in Euclidean signature and in the thermal theory. So in more detail, I want to calculate these kinds of, well, of expectation values of a bunch of operators, and I compute this as a path integral over the Schwarzian, where I insert the Schwarzian action in my path integral here, and I have some operators. Now, it is convenient when doing these calculations to switch between the Poincaré f that we have here, this big F, and a new small f that we have here, and they're related by a tangent transformation. And if you remember from the beginning, in Lorentzian signature, a hyperbolic tangent transformation was precisely the transformation relating the Poincaré to the black hole frame. So this is now rewriting everything in terms of reparametrizations, not of the Poincaré frame, but reparametrizations of the black hole frame. And well, when I write it like this small f as a function of tau is now a reparametrization of the thermal circle. So I have I'm doing a Euclidean thermal calculation, which means I'm considering a disk, a thermal disk, which is this red line here. And then I have this wiggly boundary curve that's close to this boundary that describes the Schwarzian dynamics. So this is the Euclidean thermal story or the analog of the Lorentzian picture that we had earlier. But now I want to do it fully quantum mechanically. I want to do the path integral over this degree of freedom. Now you immediately ask then, how do you actually compute with this action? So because the Schwarzian derivative, of course, is higher derivative, this looks like a very complicated problem. Now, the first idea you might get is to do perturbation theory, where you would expand f of tau around its saddle, which would be tau, plus some fluctuation epsilon of tau, and then you insert this in here, and you distill the propagator and vertices and so on. And this was applied, for instance, to the partition function, so where I do not have operator insertions in the Schwarzian theory. I haven't, by the way, I haven't yet told you what these operator insertions are, so I will tell you that in the next slide. So this is just the partition function, so we don't have operator insertions. So if you do the calculation for that at the 3 level and 1 loop, of course you have just this formula. You need to calculate these objects here, and this is the answer you find as a function of beta, where beta is the length of this Euclidean disk, which is the inverse temperature, the boundary length of this Euclidean disk. Now, Stanford and Witten have actually demonstrated in 2017 that the Schwarzian partition function is 1 loop exact. So you can stop here. You don't have to think about multi-loop corrections to this. They all vanish order by order in this epsilon expansion. So this is the full answer. So I've written it again here. So this is the thermal disk partition function. If we inverse Laplace transform this, we get this answer from which we can read off the density of states as sinh 2 pi square root e. Now it is interesting to compare this to the classical black hole solution we had in the beginning by looking at the thermodynamic limit, or the saddle, which you can get by just setting ds dE equals beta at large E, and you find that the saddle of this integral appears when the temperature is proportional to the square root of the energy, which precisely matches with the semi-classical JT black hole first law we had in the beginning for the classical black hole. But well, the saddle is invalidated at small energy, so this is the full quantum mechanical partition function that has this semi-classical limit of the classical black hole that we saw in the beginning. So now I want to go beyond the partition function and think about operator insertions. So I have to tell you what these operators are that I want to insert in the Schwarzian path integral. And to get some inspiration, let's first consider a massive scalar field in the bulk of ADS2 and consider its asymptotic expansion. So we take a massive scalar field phi, we solve its wave equation, and this is just a standard ADS CFT dictionary that you use here. You write the field in terms of its boundary values. But now the interesting thing in this model is that we can either do this for the Poincaré coordinates or for these proper time and proper radial coordinates that we have here. And if we transfer everything to these proper time coordinates, we write the asymptotic expansion like this instead of this one. And then the generating functionals for boundary 2-point functions, or for boundary correlators, I should say. So generically in ADS CFT, this looks like this. So now we just transfer to these proper time coordinates. We plug in that f is a function of tau in this case, and then we find that this object here is the reparametrized boundary CFT 2-point function. And it is this object that we will insert in the Schwarzian path integral, because this object here, so I've written it again here, is now, well, it's a functional of f of tau, of the Schwarzian degree of freedom that we are doing the path integral over. So we insert several of these objects in our Schwarzian path integral. In this last equality, I have rewritten everything in terms of this small f, and the big F and small f were related by a tangent transformation, as you may recall. So this operator is a bilocal operator. It depends on 2 times, tau 1 and tau 2. And it's also parameterized by this number h, which was the conformal weight of the original CFT operator that you started with. Now, this operator is very natural from the Schwarzian perspective. But there is also another origin of this operator that I would like to mention. You can get this operator by considering a boundary anchored Wilson line in the first order gauge theoretic BF formulation of JT gravity. So there is a first order formulation in terms of a gauge theory. And in that gauge theory, you can consider Wilson lines. And if you consider a Wilson line for which the 2 points are anchored at the boundary, this automatically defines an operator that is also bilocal. And well, you can show that this matches with this operator if you go back to the gravitational language. So this was done in these papers.
One question, this SL2R gauge theory, if you try to get it from the 3D perspective, is that the,
yeah, it's the same story. So 3-dimensional gravity is SL2R times SL2R transimals. If you dimensionally reduce that entire story, you get this. Okay, so now I still need to tell you how you actually calculate the Schwarzian path integral with these complicated bilocal operators in them. So several approaches have been developed. So I just give you a brief overview, so I won't go into any of the details here, but they all consist of relating the Schwarzian model to other dynamical models that we already knew how to solve beforehand. So you can relate it to Leo field theory, to 1D or to even 2D Leo field theory between branes. You can exploit this gauge theoretic first order perspective to calculate the amplitudes. And there are also other approaches that I show you here, which were explored during the past 5 years or so. So I won't go into any of the details. I'll just show you several of the answers and try to explain some of the gravitational physics that is hidden in these expressions. So this is the simplest one. So this is the real-time 2-point function where you have a single one of these bilocal insertions. So a single bilocal operator with endpoints at 0 and at t. So this is a function of t. And then you do the Schwarzian path integral over this object using one of these methods that I mentioned on the previous slide. And this is the answer you get. So it's a double integral over 2 energy variables, E1 and E2. Both of these have the same sinh measure that the partition function had. And then there are these Boltzmann and Hamiltonian propagation factors appearing here. And then finally, there is this piece. So this is a bunch of gamma functions. The plus minus signs here mean you have to take the product of all cases. So there's a product of 4 gamma functions in the numerator here. And this last piece is a thing that couples these 2 integrals and makes the entire calculation non-trivial to do. But this is the real-time 2-point function. So with one bilocal operator inserted. Now, as a check, if you take the semi-classical limit where you turn off gravitational fluctuations, and as I mentioned in the beginning, this happens at large C, large big C, then this thing goes to this object, which is of course the classical boundary 2-point function you would have in thermal ADS CFT. Now, it is interesting to look at the behavior of the full quantum expression here as a function of time. And what you find is that this thing is always decaying, and the late time behavior of this exact correlator, that one gets strong quantum gravitational fluctuations. So this matches that in the IR, quantum gravity is strong in this model. And in particular, it has a power law decay as 1 over t to the cubed. Instead of the exponential decay you would get in the semi-classical limit. So the semi-classical object here would decay exponentially at late times, while this exact expression decays only with the power law. So this is the physics in this object. Now, as an application of what you can do with this object, I want to mention that, you can use it to analyze one aspect of the complexity equals volume conjecture. So this was, studied by Susskind and collaborators a while back. And it states that the complexity of a boundary theory at a time t can be calculated in classical gravity as the volume of an extremal surface anchored at the boundary at points at the same time t that you want to calculate the complexity for. So in the thermophile double state, this is the calculation you want to be doing. You want to calculate the volume of this red extremal surface here. And then in classical gravity, you can do the calculation and you find that that complexity, geometrically calculated in this way, increases linearly in time because the length of this wormhole keeps on increasing. So this was the complexity story as we know, how it appears in classical gravity. So we can apply this to quantum gravity in JT because in JT, the geometry is fixed to ADS2, as I mentioned before. The only thing we have are these wiggly boundary curves here. So for an arbitrary shape of the wiggly boundary curve, we can just calculate that extremal or the geodesic length in this case of that wormhole as a function of this reparametrization f of tau. And you find this renormalized value of that geodesic length. You can insert that object in the Schwarzian path integral, so you can do the quantum gravitational fluctuations exactly. using some trick. And what you find after you do the calculation is that that complexity increases in exactly the same way at late times, even after classical gravity fails. So this is already including quantum gravity, and the complexity still increases linearly. So this is an extension of the classical regime here. Now, a question you might have here is how you would get in this complexity analysis to the complexity plateau. Presumably, this has something to do with higher topology and random matrices. So I will have something, well, I will have a lot to say in the last part of my talk about this, but not for this complexity. So I think this is an open question on how you can explain this, presumably using techniques coming from here. So as a last example of these boundary correlators, I want to just show you the out of time ordered 4-point correlator as a more complicated example. So where you take, in this case, 2 of these bilocal operators, but you put the operator legs, let's say, at an out of time ordered fashion. So again, you can do the calculation in the Schwarzian theory exactly, and it's a very complicated expression. I just show it here to see, or to show you that it is concrete, but it's complicated. But this thing has a well-known gravitational semi-classical interpretation, which was beautifully shown by papers by Schenker and Stanford 5 years ago, where the out-of-time ordered correlation function in the boundary theory captures the bulk gravitational shockwave behavior. And indeed, this complicated expression here, you can take the semi-classical regime of this object, and it indeed fully gives you the Dreit-Hooft iconal shockwave expressions. But this thing goes beyond this shockwave scattering. It contains the full gravitational answer to the out-of-time ordered correlation function. So this was just another example. Now, in the last part of my talk, I want to be talking about higher topology and multi-boundary amplitudes. So let's go back to our JT path integral. We start with the path integral over all metrics and the dilaton field, and we have the JT and the boundary action, of course. Again, we do the path integral over the dilaton field. It brings down this delta functional on the Ricci scalar. And then the story up to this point was that we considered this path integral on a manifold with a holographic boundary, which then leads to a non-trivial boundary dynamics described by the Schwarzian action. But there's also a second thing we can do. We can consider this path integral on a manifold that has only geodesic boundaries or has no boundaries, for instance. And on a geodesic boundary, the extrinsic curvature trace is 0. And the boundary action was the Gibbons-Hawking boundary action, which just had this extrinsic curvature in it. So that one will be 0. And if you consider this path integral on a manifold with only these geodesic boundaries, the remaining path integral, which is just the integral over all metrics mod small diffeomorphisms with a fixed value of the Ricci scalar, and the integrand is just the number 1, this is literally computing the volume integral of all equivalent metrics one can put on a 2D manifold with given value of Ricci scalar and given geodesic boundaries. And this is an object that mathematicians call the volume of a moduli space of Riemann surfaces, or the Weil-Petersson volume. Now, before I continue with this story, I have to sort of refine the action that we start with. So in order to analyze higher topology, I will augment our JT action by the Einstein-Hilbert action, which was topological. So I have the Einstein-Hilbert action here. I have some prefactor that I call S0. The Einstein-Hilbert action just evaluates to the Euler characteristic, which is 2 minus 2 times genus minus the number of boundaries. And this gives you a weighing of the amplitudes with topology, and in particular, a suppression of higher topology for a given number of boundaries. So that's what the Einstein-Hilbert action is doing. This is just the same as happens in worldsheet string theory. The motivation for doing this, or for reinstating this Einstein-Hilbert action, is that this actually comes from the 0th order term if you do the near extremal near horizon expansion of a higher dimensional black hole. So at 0th order in that expansion, you get Einstein-Hilbert. At first order, you get JT, and then you get an infinite series of higher corrections as you move back from the near horizon, near extremal approximation. And in that case, this S0 would be literally the extremal black hole entropy. So that's why I call it S0 here. So it's the number that causes this weighing of different topologies. So now I will show you how you calculate these multi-boundary amplitudes in JT gravity, following this seminal work by Saad, Schenker, and Stanford from 2019. So what I've drawn here is a generic multi-boundary amplitude. So I have boundaries with length beta 1, beta 2, up to beta n, and some complicated higher topological thing in the middle where I can have an arbitrary number of handles on it and so on. So I want to calculate this Euclidean amplitude in JT gravity. And what Schenker and Stanford have taught us is that you can calculate it in this way. So you have e to the chi S0. So this is just the weighing coming from the Einstein-Hilbert action, the weighing with topology. And then you have an n-fold integral over b parameters, b1 up to bn. And these b parameters, they are geodesic length of all of these tubes that you have here. Then you have a piece of an amplitude that is associated to each b and the beta that's attached to it. And then this object here that only depends on the b's. So let me describe these ingredients in a little bit more detail. So this ZJT of beta and b, this is a single trumpet partition function in JT gravity, and you can calculate it exactly. So I won't do that here. But this is the answer of that. So it's just a function of the outer length beta, and then the geodesic length that is further in the middle here. And then you integrate over these b's with a specific measure dB times b. So this multiplicative factor b, this arises because you can glue these tubes together. You can glue the two ends of these tubes together with a twist, and that twist can range from 0 all the way to b, where b is the geodesic length again. So this gives you this factor of b here. And the geodesic length is integrated from 0 to infinity to sum over all possible geodesic lengths with which you can glue these surfaces together. And then finally, this interior object that you have here, this is the Weil-Petersson volume. So it's a function of all of the b's. It's an amplitude that is that only has geodesic lengths or geodesic boundaries, as I mentioned a couple of slides ago. And this is calculating the volume of the moduli space of Riemann surfaces of genus G with n geodesic boundaries of length b1 up to bn. And this is known to be a multivariate polynomial in the bi squared. So this is the gravitational calculation you can do. Now, one of the most interesting aspects of Schenker and Stanford's story is that they showed that the full JT gravity, so including all of these higher topological amplitudes, is as a whole a matrix integral. So let me briefly give you a historic overview of these arguments that led to this statement. So in 2007, Mirzakhani famously showed that these Weil-Petersson volumes, that they satisfy recursion relations. And this is actually a simple way to actually calculate them. And then in the same year, Hénard and Orantin showed that these recursion relations, that they actually match with the topological recursion relations of a double-scaled matrix model with the leading spectral density that is basically singed to pi square root e. So this is the JT disk spectral density that we have here. And there are objects in this double-scale matrix model called topological recursion relations that match with these recursion relations you have for the Weil-Petersson volumes. And then, well, I will skip all the way up to where we are now. So then Schenker and Stanford stated that JT gravity is a matrix integral by combining these facts together and generalizing them to JT gravity as a whole. And if you define in the matrix integral macroscopic loop operators, which are trace e to the minus beta h, where h is the random matrix of the matrix model now. And if you insert multiple of these objects in a matrix integral calculation, so these angular brackets here, I mean just do the matrix integral. So schematically, you need to do this thing where you insert all of these trace e to the minus beta h and then do the matrix integral over h. This multi-loop correlator in the matrix integral with the above leading spectral density is directly identifiable as these multi-boundary amplitudes you would calculate in gravity. So using these Weil-Petersson volumes and these JT single trumpet calculations and so on. So this matrix calculation matches with the same calculation you would actually do in gravity. And in this, yes.
Yeah, so and this is JT gravity without the Schwarzian axiom, right? Without the Schwarzian particle.
The Schwarzian is there. It lives at the boundaries. So at all of these asymptotic boundaries, these are holographic boundaries. There you have Schwarzian degrees of freedom. But this story is more complicated because you also have these topological things happening here. So this combines the Schwarzian analysis with this higher topology stuff.
But here the boundaries are geodesic. Right?
These B's, these black boundaries here, these are geodesic, but the red ones, they're not geodesic.
The betas are not geodesics.
Yeah, these are just asymptotic holographic boundaries that I have been talking about in the beginning.
Okay, yeah.
Yeah, I should have said that actually. Okay, so in this dictionary between the matrix integral and between the gravitational calculations of JT gravity, the double-scaled expansion parameter of the matrix integral, so I called it L here, it matches with this e to the S0, where S0 is this extremal entropy. So that object serves as a double-scaling expansion parameter. And this entire story has a holographic interpretation where the boundary Hamiltonian is directly, or is to be directly identified with this random matrix H. So this is not an ordinary version of holography. This is a version of an ensemble averaged holography, because we don't know anything. Well, we don't know the specifics of this Hamiltonian. It's not fixed. It's randomized because it is the random matrix. And you should compare this, for instance, to SYK, which has some averaging going on in it. The coupling constants in the coupling in the SYK model is averaged, but this thing is even more extreme. In this case, the entire matrix is averaged. So this is the interpretation of this. Now, as a final application,
Thomas,
yes.
Just to warn you that you have been talking for 45 minutes. Okay.
Okay. So I have 5 more minutes, I guess.
Yeah, something like that.
Okay. Well, this is the final application, basically, that I want to talk about of this JT gravity is a random matrix integral, which is Maldacena's version of the information paradox in ADS-TFT. So the boundary two. So I'll first briefly remind you on what this information paradox, or what this version of the information paradox actually is. So the boundary 2-point function in thermal ADS-CFT, it decays exponentially at late times. So I already showed you that kind of expression. So at late times, this decays exponentially. And even after you do the Schwarzian path integral, it still decays uniformly. In this case, it was as a power law, as I mentioned earlier. But both of these statements are not compatible with having a finite entropy boundary system that would have a discrete spectrum. So if I have this boundary 2-point function and I insert complete sets of energy eigenstates for a discrete system, it would look like this. And this would oscillate erratically at late times around a non-zero mean. And in particular, this would never really decay to zero, which these gravitational calculations would do. So, well, the question is, how do you explain this aspect of the boundary system from bulk gravity? That is basically this version of, or Maldacena's version of an information paradox. Now, to address this, we will do a simplification because we expect these matrix elements of these boundary operators, at least for simple operators, to behave rather smoothly as a function of the energy. So this is basically a version of the ETH conjecture. And we drop these factors here, which means we reduce this thing to an object that is called a spectral form factor, and that was extensively studied in many papers, and these papers in particular, which is basically the mod squared of an analytically continued partition function. So we take z of beta plus it times z of beta minus it. Well, for a discrete system, it looks like this. This thing has a late time mean that is non-zero, which you can check explicitly. And this contradicts, again, this gravitational calculation. So I want to focus on the spectral form factor, which is a simplified version of the boundary 2-point function, because you basically drop this dynamical information and focus just on the energy statistics, basically. Now, this spectral form factor has a typical form in a chaotic system. And what I've plotted here is the form of this, or well, the shape of the spectral form factor for an averaged chaotic system. So this is a log-log plot as a function of time. And after an initial sort of transient behavior here, this is expected to show, well, a slope, dip, ramp, and plateau region. So this is the late time behavior of the spectral form factor, basically, which is generically expected to appear in chaotic systems. Now, what I will show you in the last couple of minutes is that JT gravity has precisely such a late time behavior for its spectral form factor, which can be easily proved using its matrix description, and which also has a gravitational interpretation in terms of higher topology. And this is the aspect that I will mention now. So because JT is a matrix integral, within a matrix integral, the spectral form factor is this, this matrix integral calculation where I insert two operators, two analytically continued macroscopic loop operators. So this is the calculation in the matrix. On the matrix side, you would want to do. Now, this calculation is related to the pair density correlator, where I basically Laplace transform these loop operators in terms of spectral densities. So this is, this is double Laplace transform into this equation. And then, you basically need to know what this pair density correlator is in this matrix ensemble. Now, if you have a Gaussian unitary ensemble, this has a very familiar form. So I've written it out here. So the first piece would be a disconnected piece where the two, let's say the two energies don't talk to each other. then these two terms, they combine to the famous sine kernel, but I've written them out separated here because they will have a separate geometric interpretation later on. But these two terms, they form the sine kernel in random matrix theory. And then you have a contact term here. So this expansion only holds, of course, when this double scaling parameter is very large. So in this case, e to the S0 would be very large. Now, an important point on this form here is that this thing, or this expansion, is actually expected to be universal for Hermitian random matrix systems, at least away from the spectral edge, and when the energy separation between the two energies here is sufficiently small. So whereas, well, I first wrote this down for the specific Gaussian unitary ensemble, this is expected to be quite universal in a suitable range of the parameters. So we expect this expression to hold for JT gravity as well. Now, in particular, if you look at this expression, because rho 0 of E, which is just a singe spectral density, but with a factor e to the S0 in front, you expect this one to dominate as e to the 2S0, because these two things, for instance, don't even have an e to the S0 up front, and this one only has one. However, at very late times, where times are of the order are exponential in the entropy, by Heisenberg, this means very small energy separations, you can see that this can compensate the suppression and give very important effects, because if the energy separation is of the same order, then there's a competition between this leading term and these subleading terms here. So with all of this, we can understand the late time behavior of the spectral form factor in JT gravity. So the first piece is the slope piece in this late time behavior, and this arises from this factorized contribution of the pair density correlator. So basically, this just comes from the product of two of these analytically continued partition functions. We have already calculated them. So this is the Schwarzian calculation or the disk calculation. And this gives you a 1/t³ decay. So this is the slope region. In a log plot, this will be a linear decrease. And as I mentioned, geometrically, this matches with two disconnected disk geometries. And this is also the late time decay that we found in the Schwarzian regime. So the Schwarzian late time regime is this slope regime in the very late time behavior of this, of the boundary 2-point function or of the spectral form factor in this case. And then we need to explain the ramp. Now I have split the sine kernel in two pieces, and the first one was this piece. If you Fourier transform that thing, you get a linear growth in time. So this is the ramp region. This is where this spectral form factor goes up again after the slope. And geometrically, you can get this by doing this calculation where you take two disks and you connect them with one tube. So this is the geometrical calculation you can do by doing this integral over geodesic lengths and so on. So I'll skip the details. And this matches with this linear growth here.
Now, one minute, Thomas.
Okay. I'm almost done. So you can also determine this dip time. This is where the slope and the ramp intersect. So this is like the minimum of that curve that we had earlier. You can calculate it explicitly in this model then. And then finally, you need to explain the plateau piece. And this comes from this second contribution to the sine kernel. So I split the sine kernel in two. This was the second piece. Now this piece is non-perturbative in e to the minus S0. And this happens because rho of e has an e to the S0 in it, but there's a cosine in front of it. So this is going like e to the I, e to the S0. And if you would go back from, so this is non-perturbative in the genus expansion or in the e to the minus S0 expansion. But if you would go back to our original theory, where S0 and Newton's constant are actually related like this, then this kind of object would be doubly non-perturbative in the expansion in Newton's constant. Now, if you Fourier transform this, you get a linear downward piece, which precisely cancels the linear upward piece that the ramp gave you, and it causes a leveling off of the curve, starting at the plateau time, which would be this time. And there's a geometrical interpretation for this in terms of deep brain effect with additional boundaries in the gravitational bulk. But I think it's fair to say that there's no full understanding on how this, or no full picture yet on how this all works, on how this non-perturbative stuff works. And finally, the height of the plateau itself is determined by this final term we had in the pair density correlator, this contact term. Well, I wanted to make some comments, but let me skip those. Maybe just stating that you can reinstate these matrix elements and study the boundary 2-point function. This was studied in a couple of papers as well, and leads to a similar picture of slope, ramp, plateau. As a final comment, there are generalizations you can study of JT gravity. So in the past year, there have been studies of deformations of JT gravity, where you add to the linear dilaton potential these kinds of exponentially damped contributions. You can also study the older minimal string theory as a dilaton gravity, which leads to a dilaton potential, which is a hyperbolic sine function. Both of these can be shown to be described also in terms of matrix integrals, which means you expect the same kind of explanations for the late time behavior, so slope, ramp, plateau of holographic correlators. And then finally, you can ask about what about higher dimensions? So for instance, for 3D pure gravity, there is a construction of this double trumpet amplitude. So that was a thing that in JT gravity gave you this ramp region of the late time behavior by Kotler and Jensen in 3D. But there is no understanding of the generic topological expansion in 3D. And then the final comment here is that the textbook case of holography, ADS 5 times S5 type 2B superstrings, dual to n equals 4 super young mills, that one has a fixed boundary Hamiltonian, which means no ensemble averaging, which suggests that there are no connected topologies, because these connected topologies, they appear because of the matrix integral. So there is some tension here, and this is unresolved at the moment, or it's not well understood how these different versions of holography all fit together. So to summarize, JT gravity is a toy model of quantum gravity, which is both relevant for many reasons and also solvable, which makes it very interesting. And it allows us to address open questions in quantum gravity, such as making contact with the information paradox and remnants of discreteness in the bulk. And so I believe that JT gravity is an ideal test case model to study some of these conceptual questions about quantum gravity. So thank you.
Okay. Thank you. Please, those who have questions, just ask.
Yeah, I have a question.
Go ahead, Pepe.
So when you mention the computation of complexity in JT gravity, is it implicit the choice of a state? Like I'm computing the complexity with quantum corrections of what state?
Well, so the pictures that I drew were for the thermophile double state.
Okay, so is the thermophile double state?
Well, geometrically, I just did the calculation for the eternal black hole, which would correspond to the thermophile double state. So,
well, I mean in the JT gravity case, in the second picture.
Yeah, but yeah, it is the same. It is the same state. Yes.
So if it is, then am I supposed to interpret this as an ensemble average of?
So this was not done with the ensemble averaging. That is an open question. This was just with fixed topology, or just a Schwarzian result, or just the disk result.
Yes, but even if you take the disk result in the analysis of Witten and Stanford, they claim that the natural interpretation of that is already an ensemble average before you think about higher topologies. So ultimately, am I going to interpret this, or should I interpret this as an ensemble average or not? Just
even this calculation, you mean? In what sense do you mean that this is already an ensemble average before?
Well, if it is the thermophile double state, it depends on the Hamiltonian.
Yes.
But if I'm instructed to average over Hamiltonians, then
well, but you mean because
I'm just asking what is the standard interpretation of this calculation as being quantum?
Well, okay, so these kinds of things are just you fix the boundary, but you do the path integral for all gravitational fluctuations in the middle. In this case, they only restrict to boundary graviton fluctuations because that's the only dynamics you have, and you do the path integral for all of these fluctuations, which means you keep this, or you do the path integral or the sum over all of these wiggles of this boundary curve and weigh it with the Schwarzian action. That's the calculation that I'm sketching here.
Okay. I still think that my question is non-trivial, but I don't know what.
Yeah, I don't know what to say.
Okay.
Okay, more questions?
Yeah, can I have a question?
Sure.
Can you use the matrix integral spectral form factor to compute gravity quasi-normal modes?
You mean like because quasi-normal modes are already classical, right?
That's right. That's why I'm asking if you can do it from the matrix integral point of view.
But the matrix integral is giving you heavily quantum mechanical aspects of gravity. If you want to restrict to the classical piece, you don't even need these higher topology stuff. You just need the disk result. And then for the quasi-normal modes, you don't even need the Schwarzian path integral. You can just do the classical gravity calculation. Now, you can't see the quasi-normal modes in this ADS2 geometry explicitly. So I didn't mention this, but so this kind of 2-point function. So this was the boundary 2-point function using the Schwarzian integral, so only disk topologies. And when you go from here, when you prove that this gives you this semi-classical limit, along the way you can distill the quasi-normal modes basically. Basically because this expression gets Fourier transformed in an expression for which you can read off the quasi-normal modes. And the quasi-normal modes appear as poles of these gamma functions that you have here. Yeah. So in a sense, you can even try to interpret them in this full expression as some sort of quantum generalization of that, because they give you poles in the amplitude, because of these gamma functions.
So higher topologies would give corrections or not?
They would give corrections to these kinds of amplitudes, but I don't know. Well, I don't know whether you would want to interpret these still as quasi-normal. It depends on your definition. If I use the definition that these are just the poles of these gamma functions in the complex energy plane, then I can give you a generalization of this, even just at the disk level. But yeah, if you want to trace this back to solving a wave equation in an ADS black hole geometry with suitable boundary conditions at the horizon and so on, then yeah.
Okay, thanks.
Okay, any more questions?
Can you comment about the supersymmetric extensions or supersymmetric versions?
Yes, so you have supersymmetric versions of all of these, n equals 1, n equals 2, and so on. So you have super Schwarzians and super JT gravity, and they have all been studied as well. Lots of what I said here extends to that as well, or has been understood, but some aspects have not been cleared up as extensively as in the bosonic case. So for instance, all of these higher topology stuff that was clarified in a long paper by Stanford and Witten from last year. And how it relates to a matrix integral and so on.
The matrix integral, of course, there's not a supersymmetric version of that, right? I mean,
well, these bosonic versions, they basically reduce to the 3 Dyson ensembles. So this one reduces to the unitary one, basically. And if you were to consider unoriented bulk geometries as well, you can go to the orthogonal and symplectic ensembles. And then the supersymmetric cases would correspond to all of these other matrix ensembles, these Altland-Zirnbauer ensembles. So they generalize the Dyson ensembles into other sort of universality classes, and they would be relevant for the supersymmetric, for the supergravity case. And that is explained in that paper from Stanford and Witten from last year.
Okay, I think there is no more time for questions. So let's thank Thomas again.